So now I'm going to cover stress concentrations, and I have a plate that's under uniaxial load with a hole in there. And that's where the previous ideas are helpful in this case. So to remind you, the stress-strain relationships are given by this. And you can see here, I can relate stress to strain in a fairly straightforward manner. That's your constitutive law. And I can find the modulus and Poisson ratio doing testing. So that's a fairly easy thing to do for any material, for most materials. And then we have the stresses in terms of area stress function, and then the bar harmonic equation. So if you recall, the area stress function provides a methodology or an approach to solving problems that otherwise may be very challenging to solve. By selecting an appropriate area stress function that satisfies the bar harmonic equation, you automatically satisfy the equilibrium equations and the compatibility equations. And not only that, you can relate the stresses to the area stress function in this manner here. And if you know the stresses, then you can calculate the strains through the constitutive law. And if you know the strains, then you can know what the deflections are, because you can relate the strains to the deflections. So let's study the following question. What are the stresses at the hole for this case? And the answer is that this problem is way harder, right? Way harder, but it's still doable. Well, I'm going to use the idea that I discussed in the previous lecture, which is what are the boundary conditions? In the far field, earlier I had used sigma naught, but sigma naught is the same as T in my notes. In this case, and this is what I had used earlier, I just used sigma naught, but the equations you see here are the same as I described in the earlier lecture for the uniaxial case with no hole. So in the far field stress, the radial stress, the stress in the theta direction, and the shear stress has to be equal to this by using the coordinate transformations I had discussed earlier. And to recall, the coordinate transformations I'm talking about is the case that you see here, where the far field stress is sigma naught, and what I'm doing is everything else is zero here, so you find that this is the states of stress in the polar coordinate system, and that's equivalent to the Cartesian coordinate system with sigma naught being in the x direction. So I haven't done anything different. What I did here, though, is I wrote sigma radial, the radial in the stress in the radial direction, the stress in the tangential direction, and the shear stress, I rewrote them so they're in terms of the far field stress but in the polar coordinate system. The second thing you notice here is that I have this condition here. And what is that condition saying? That condition is saying that at the hole here, I'm not applying any pressure. Because I'm not applying any pressure, there's no tractions there. So I can use Cauchy's relationship, which states that I have tractions equals stress times the normal to the surface, and in the polar coordinate system, n is 1, 0, and the tractions are 0 because I'm not applying any pressure inside. And because of that, you can find that these conditions won't be met, that there's no radial stress and there's no shear stress. So that makes our life a little bit easier there. And you can see I have 5 total boundary conditions, 2 here, 1, 1, and 1, 5. And for this particular problem, the area stress function that has been proposed that actually solves this problem is this particular one. This area stress function does a very good job of solving this problem. You can show that this area stress function will satisfy the bar harmonic equation. And the other reason this area stress function works is that the presence of the hole acts to disturb the uniform field. So you expect that this disturbance, this hole here, is local in nature, But as you go far away from the hole, that particular disturbance effects are gone. And this actually does a good job of taking care of that behavior. And so, and also you notice that this problem is not axisymmetric, meaning that as theta, as you move around the circumference theta, the behavior of the stress field should be different as you go around the hole. That makes sense because the tractions are only applied in the x direction. And that's where the cosine 2 theta term matters. And that's why we have this r squared term and this r, because as you go far from the field, you'll expect some of these terms not to contribute. So the next step then is, if I know the area stress function as it was provided to us, somebody actually worked on this to figure out what these are, and I can actually show you how this area stress function was developed, and I can do that by providing to you a supplementary note, which I will not cover right now here. If I plug in this v in here now into each of this, I can get the expressions of sigma r, sigma theta theta, and sigma r theta as a function of phi. And what you get is this expression here. So given the area stress function, sigma r, sigma theta theta, and sigma r theta become the expression there. Where A naught, A1, A2, A3, A21, A22, A23, A24 are unknown at the moment. And so then I'll continue here. For us to have finite stresses far from the hole, I cannot have this r to the 4 because that r to the 4 means I will have infinite stresses when r goes to infinity. And I have to have finite stresses. The same thing happens with the log of r. This term right here will blow up. So A3 and A22 must be 0. So I don't have infinite stresses far from the hole. So I'm able to find those coefficients for now. Now we'll apply the boundary conditions. And the boundary conditions, I have 5 of them. And if you notice here, I have 5 constants that are unknown. So 2 of them are 0 by inspection, because these stresses cannot be infinite when r goes to infinity. That doesn't make sense. So I'll apply these boundary conditions. It needs to satisfy these ones. There's 5 of them here. And when you do that, you get a system of equations. You have 5 equations and 5 unknowns. When you apply these boundary conditions, these 5 boundary conditions to these 3 equations, you get basically 5 equations and 5 unknowns right here. And so you can solve them for each of the coefficients that were unknown. Over here, you can see them here at the bottom. And once you know these coefficients, you can plug them back in here into this equation here. I made a mess now, but I can plug it back into these equations. And when you do, you get the stresses as a function of the far field stress T, which I am also using sigma naught in these lectures. And so the thing I want to point out is that that is the solution for the stress states near the hole. Very, very cool. I know now how the stress varies near the hole when a stress field is occurring in this body of material. The second thing to note is that this area stress function can be verified to satisfy the biharmonic equation. So therefore, you're not only satisfying the equilibrium equations, you're also satisfying the compatibility equations automatically. And that shows you the power of the area stress function. Very powerful idea. And you can see that we've done something that's really, really cool, which is, if I know the radius A of that hole, and I know the far field stress T, and I know And I can then vary R from R equals A, and in any direction I can look at it, and I can tell you how the stress states change near the hole, which is incredible. It's a great design tool because in real life, I'm going to have a fuselage, and that fuselage may have rivets or may have open holes, right? But if it's, this is telling us, if I know the far field stress in one direction, I can tell you what the stress field looks like without having to use finite elements. I don't need a computer code to do these calculations. I can just open the book and calculate it. So let me move forward then to what this looks like later on. So now I'm going to use a different convention. I'm using S here. That's okay. But these equations here that I'm showing you are the same equations as these ones. I'm changing convention. R naught is a radius of the circle. Here I was using A. T here was sigma S here. And then I have R, which is a radial coordinate. That's the same thing I'm using here. The stress states are as you show above. You find that along the edge of the circular hole, sigma RR and sigma R theta are 0. But what you also notice is that sigma theta theta varies as you go around the hole. You notice that at the hole, if I plug in the value of R equals R naught, which is right at the hole, because that's where that's where you expect failure. You expect failure right at the hole. R equals R naught gives me a value of 1 there, gives me a value of 1 there. And when you actually do that, these two cancels out. And what you find is that sigma theta theta is the stress state times 1 minus 2 cosine theta around the hole. And then you also notice that the radial stress and the sigma R theta is 0 at the hole. We know that because there's no pressure applied inside the hole. But what is so cool about this, and I think this is exciting, is that I know the variation of sigma theta theta as you go around the hole. You can actually plot it, right? You can do a plot. I'm not going to do it here, but you can so okay, sigma theta theta as a function of theta around the hole from 0 to 360, right? We can use 2 pi, right? You can plot how that stress distribution looks like. So if I choose the value of theta equals 0, let's say this point here, that's theta equals 0. Let's choose a different color so you can see it. Let's choose this point here. That point is theta equals 0. So if I put theta 0 here, I get that sigma theta theta, which is the stress going tangential to the hole. That stress right there actually gives me a value of minus S, which is not what you have expected. So what we're discussing then is that sigma theta theta, the hoop stress, is minus S at the hole. But when I look at theta equals 90 degrees, which is over here, now the hoop stress is going this way. That's the hoop stress we're talking about. That theta there is pi half. And what is very cool about that, let's look at that one. So theta equals pi half. What happens there? So I get S sigma theta theta equals S 1 minus 2 cosine 2 theta. So 2 times pi half is pi, and cosine of pi is minus 1. So you actually get 3 times S, meaning that the stress field, this stress here, that's tangential to the hole, sigma theta theta, is actually going to be a stress that's 3 times higher than the far field stress you see here. And so the stress concentration at the hole is three times higher. And then I already covered the fact that the stress field in this direction, sigma RR, is minus S. So what is interesting is, and you wonder why that is, right? So let me plot what is happening to the hole. When I apply a load, and that's not a very good picture of a hole. So let's try again. A little bit better. I apply a far field stress. What happens to the hole is a hole elongates. But in this direction, it's going to contract. In this direction, it's contracting. In the other direction, is extending. So it makes sense to me that this stress is negative S. And so continuing on then, to summarize then, you have this as a stress field at the bottom left. You can see the stress sigma theta theta. What I'm trying to show here is sigma theta theta will drop as you go in the y direction. The hoop stress there. And here sigma theta theta is always tangential to the hole because that's the direction in the polar coordinate system. You also notice that I'm showing the equations on the right as well, so you can see them. And yeah, what is cool is that the highest stress is at the hole and it's 3 times the remote stress. Finally, if you were to plot it, so you can see what it looks like, what I'm showing you here that may not be obvious is what does the stress field look if you were to plot it? And what you see here is that the stress field will look actually like that. Very complex stress field, but the stress concentration is 3. And so that concludes this particular lecture. Now let's start with combined cases.